Good evening, everyone. Welcome to our week 4 review session for business analytics. How has everyone been doing in the past week?
Wonderful.
Oh. Glad to hear that.
No, I wasn't telling the truth.
I'm not sure what that means. In week 4, we have learned about more regression. In this case, we build on what we learned in the past week about simple linear regression, where the predictor has only one variable, to multiple linear regression, where we can add more predictors to the model. Are there any conceptual difficulties and questions you have encountered in the past week?
Yeah, I sent you an email. I was struggling. I don't know how you want to go about it, but I was struggling with 2E. I had like 3 different models, and I sent you. I think I sent you my regression equation.
Mm-hmm.
So I guess I don't know. Without giving the answers away, do you have a visual graph of what that should be? I struggled with what to put on the x-axis versus the y-axis, and I think 2 variables is right, just one independent and obviously one dependent.
Oh, excuse me. I was not sure what your question was.
Yeah, it was probably long-winded and didn't make sense, I'm guessing.
Is your question particularly corresponding to some parts in homework 4?
Yeah, so I'm trying to think now what the question was. So yeah, so I really liked my equation, and I had, in the sense that it just made sense to me, I had, the intercept then on 2E, the intercept as
Okay, oh, excuse me. Could you hold on there? What questions are you working on for when you had this problem in homework 4?
So the question was real. I think I couldn't get my average I subtracted my prediction versus my actual, and didn't get 0.
I'm not quite sure what that means. So let's take a look. For example, this is our assignment 4 in our shared screen. There are 2 questions containing multiple parts. What parts did you have the question from?
So 2E,
Oh, that's what I mean. Sorry, I was
sorry.
I was thinking what it means by 2E in the equation. Okay, now I got it. Okay, we can take a look at it. And your question was you were trying to calculate a 0 out of 2E.
Yeah, so I dumbed it down, no pun intended. So I made the dummy variable, people that were below the median, in my example, was 0, and people above the median were 1. And then I put that just to the life satisfaction score.
Okay.
And then I only had 2 prediction values. Everyone below the median was 1 value, and everyone above the median was another value. I like that because thinking that if you're
are you could I interrupt by asking, by saying that you had 2 values only, are you referring to that you have 2 values in the predictor variable? Are you talking about that you have only 2 predicted life satisfaction values?
Yeah, see, this is where I just feel like I'm off. So I had I only had 2 predicted values. So if you were below the mean,
okay, I see.
I got everyone with the same number, and I'm like, I don't know if that's right. I can show my screen if that helps.
Okay, it doesn't sound right. The reason is that you are missing 2 important variables as predictors. We can work on that very soon. How about other students? What questions did you encounter in doing problem 1 or 2?
Yeah, I encountered the same issue as Steve.
Really? Okay.
And I ran the regression model a few different ways, just trying to understand it more. And you know, in one way I had three slopes, and in another I had two. So I'm just
I see.
curious how many like coefficients you would have it.
It sounds also like a case where predictors are missing, so the setup of the regression is not complete.
I added the interaction.
Yeah, that might be the correct way to do so. We will illustrate what it means. So does that mean everyone is good on problem 1? And you mainly have questions from this part
Jerry,
in problem 2.
This is Perla. This is Perla. I actually am a little stuck on problem 2B, so I'm a little behind everyone else.
Oh, I see.
Maybe I just didn't understand the way it's worded. We have the income column, and then it says the square of income as dependent variables.
Yeah, well, here it says as independent variables. Did you so we always put independent variables among X in setting up a regression.
So how do I calculate the square of the income?
How do you calculate a square of an income using an Excel formula? It's easy. Let me show how we can calculate a square of a variable. For example, we have income. This is the first case, income as $58,000, right? And here is the square of income. We just use this symbol to represent power and 2. That's saying that we take the value of 58 and raise it by the power of 2.
Oh, okay. Okay, thank you. Yes, I did do that. Thank you. Sorry.
I see. Yeah, in such cases where you're not sure how to calculate certain quantities in Excel, always use Google search. It's quite helpful. For example, in this case, we would type Excel formula power of X. And here is some links to how to calculate power in Excel. So as it says here, highlighted, just enter a caret. Okay, wow, I got to learn a new word here. It's called a caret. Okay, in the formula bar, then enter the power, as I just illustrated. Well, great. One problem solved. Before I move on to part E, are there other questions I should keep in mind?
I think it's along the same theme that everybody else is asking for, but where I get confused is when do I use a square of something? When do I use an interaction? When do I use a quadratic? Like these are all things that we've used to add independent variables, but I'm not sure when to use them, if there's an order that I should try them in, or I know we're always looking at R squared, adjusted at R squared, but I'm just unsure where to start.
Oh, that's a great question. What you are asking about involves variable selection. So I have included in our review session notes about what variable selection means and what are some good way and bad ways to do variable selection in our week 4 discussion session, but I put it in the Beyond Course section because none of our homework questions require variable selection. So in this section, in this part, I provided reading materials about the methods and consequences of variable manipulation. Variable manipulation include cases like where we need to take a polynomial like a square of a variable, or transform variable from continuous to categorical. For example, that's what we did in problem 2 about predicting life satisfaction out of income, where we transform income from a continuous variable to a categorical variable to represent the low income group and high income group. These are all called variable manipulation. After that, we could do variable selection to see which of the manipulated variables should enter a model. That does involve some intricate process, and there are still debates about what would be the best way to do so. However, there are still lots of consensus about what are good ways versus bad ways to do variable selection. However, as what we have learned already, a good starting point is simply plotting. So based on the plot, we should have a good sense about which type of variables and which terms should enter the model, like what this scatter plot shows. We can practice on that later to see, well, okay, what it means, what we can read out of a scatter plot. Okay.
Jerry, quick question. This is Adam speaking.
Hi,
How do you plot the R square there, or the square of income, I mean, in that same plot? Do we need to do that? And if yes, how do you plot it where it makes sense?
You could, but you may not want to do so. So here in problem 2, let's take a brief look, just in case, just so we have the same understanding. In problem 2, we are trying to understand the relationship between income and happiness. Here, income is a predictor, an independent variable that goes to X. Happiness, instead, is the dependent variable that goes to Y. In this case, built upon what we learned from last week, we are adding additional predictors. And in this case, although we have only 2 variables, we could build additional variables based on them. And as what Adam just mentioned, and we just illustrated, we could square the income to form an additional variable in addition to income. When we have both income and its square, if we plot directly the income, the happiness versus income, here you notice that the income goes to the horizontal axis and the happiness goes to the vertical axis. If we plot directly only income and life satisfaction, these 2 columns, we show that the plot shows a curve. However, this most of the curve forms because of some lower values away from an otherwise linear trend line. So for example, if we remove these cases that's in the lower part around where income was $200,000, then we could possibly observe a linear trend. However, because of certain cases where the income is high, but the satisfaction is not as high as what a linear trend predicts, then we observe a curve. So does it make sense if we plot only the square and life satisfaction? I don't think so. It may not be helpful. We could still plot these 2 columns, square versus life satisfaction. It may help us to determine the coefficient of the square term, as we see here in our question 2, part B, right? Where we fit a second order polynomial model. That means we should have 2 predictors, income and the square of income. We could use a plot of a square income as horizontal axis and life satisfaction as the vertical axis to have some preliminary understanding of what the sign of square income would be in the regression model. But it doesn't provide essential meaning. The sign could be different than what we observe from the model, from the plot, sorry.
Isn't the question asking for that? Asking
No,
to plot both at the same time? If you look at it,
the question doesn't ask you to do so. Yeah.
Oh,
I'm answering your question whether it makes sense to plot square of income and life satisfaction alone, leaving the income out. Oh, okay. There are some discussion going in the chat room. Could you help me catch up with that? Are there important questions I need to address before we head up to the verbal building in part E?
So what you're saying, Jerry, is we plot what the income and
if we plot directly, no. If you plot income and square income, they simply form a what you call that? You simply form what the relationship should be between x and x squared. So what I'm saying is that to address question part A, we simply plot these two, income and life satisfaction. That's enough.
So B, is it asking? I'm still cannot get to the result. I'm not sure if I'm the only one. What is B asking for?
What is B asking for when it mentions to fit a second order polynomial model to predict life satisfaction? And also we need to address how well the model fits the data.
Using what variables? Only the income. Using what variables? Only the income?
Yes, as it says
and
here.
Life satisfaction only?
Here in question, in problem 2 part B, what we need to do is that when it says about second order polynomial, it means that in a predictor, we should have a variable and its squared version, both included. So as you can see in the parentheses, it particularly mentions that we should use income and the square of income as independent variable to predict life satisfaction. Do you see what it means?
That was my question initially. How you do that? How
do we do that?
Plot those two independent variables along with the life satisfaction.
Oh, I see. Okay. So here, when it says to fit a model, it means we need to use the regression function in Excel to generate a summary output like this.
So it's not a scatter plot?
No, the scatter plot was done in part A.
Oh, okay. That would make sense.
Yeah, so in part A, we need to generate a scatter plot to relate satisfaction with income. And to help with your understanding, it particularly says that we should have life satisfaction on y-axis and income on x-axis. I think the professor added these notes because many students previously have mistakenly switched what should be on the horizontal and vertical axis.
Jerry?
Hi.
Hi, I just have a question. I think what I'm hearing too, and perhaps it's just me, but when I look at your Excel sheet and on the far left, you have the column square of income. How do you create all those numbers? What is the formula that you use to do that?
Oh, good question. Maybe it was because you joined later. you could read what the formula was. And as I just illustrated, there's always a good way to search for how to calculate certain quantities by Google it. So here we should ask Google to tell us how to do Excel formula to calculate power of X. And that's how we calculate it. So how about we move on in question 2, because the technique required to complete problem 2 is exactly the same as what we need for problem 1. All right, upon the 2 parts we have done so far, we have shown a scatter plot of satisfaction versus income. And we just did a second order polynomial model by using Excel regression module to generate summary statistics. Following that, we need to make predictions in terms of what change would be when income increases from this much to this much, and another change from this much to this much. Have you all been able to calculate these quantities? What questions have you encountered in these 2 parts? Then we can see how we can transform income to categorical version, then use a piecewise linear regression model.
Could you maybe go over them quickly and also maybe highlight how you would like us to round our numbers?
Are you talking about an demonstration about how to address C and D part?
Yes.
Okay, great. Let's do so. All right. We have already generated a second order polynomial model by introducing income as a predictor and square of income as a second predictor. And always we have an intercept in the regression model, right? So using these coefficients generated in the summary output of a regression model, we could calculate the effects. In this case, part C and D, part C and D ask us about the change between certain quantities. So let's do it. A very convenient version is that we could calculate predicted values for certain income, right? So as what we demonstrated in our last example, when in last week homework, we have predicted house price using square footage. We use exactly the same technique to address this question. First, we need to input the values of predictors. In this case, the predictor is income and the square of income, right? So we need to use these. So here we have income. Well, let me make sure this is actually okay. So here you notice that this quantity looks very different than these quantities because the income above in our sample is recorded in thousands of dollars, whereas in the oh, interesting. Okay, whereas in our homework question, it's in dollar. So we need to transform it so Excel understands what it means by this much, because this $60,000 was originally in the question originally in dollars, so we need to transform it to in $1,000 by dividing it by 1,000. So it becomes $60. but it means 60,000. And now, how much from to what value in income should we calculate the change? This is 60,000. So in terms of how many thousands of dollars, we should put 60. Oh, we should put 70, excuse me. So we have the baseline 60,000 and target level 70,000. Now we need to calculate the difference in life satisfaction. However, what goes into the equation includes a square of income, right? So we should also calculate a square of it by using cell formula of this much raised by power of 2 using the symbol of this. All right. So we have this part set up. All right, now we have both predictors, the income and the square of income. Now, how do we do how do we calculate or predict the life satisfaction in this case? After we calculate the predicted life satisfaction, then we can take a difference between these two values. Then we can answer this question: how much change would there be in life satisfaction between these two levels of income? So to calculate the predicted life satisfaction, we simply need to use the coefficients coefficients estimated in our regression output. So because we need to continuously use it, we should use absolute reference by using the $sign. This is income. Then we need to calculate what each of the coefficients represent. In this model, it tells us that for income, the coefficient is 0.98. Using this coefficient, we need to times it by income alone. This is the income in thousands of dollars. Then we also need to add another effect from a square of income by using this coefficient. For coefficients, it's helpful to use absolute reference. For square income, we need to time square of income. For the coefficient corresponding to square income, of course, we need to multiply it by the square of income. So make sure the sequence of the predictor match that of the coefficient. All right, this would be the calculated life satisfaction. Let's review the formula or equation used to calculate life satisfaction. Notice that it's nothing but a linear combination of the coefficients here in the absolutely referenced cells and the predictors. This is income, this is square of income. So using that, we could calculate the life satisfaction when the income is 60,000 and when the income is 70,000. And we can use the difference between these two to calculate the difference. So, for example, the difference of these two values would be this much, right? About 6.2. So this would be the predicted difference. That's exactly answers what part C requests. And using the same technique, we could address part D. However, in part D, it also asks why the answer was different from part C. So
could you please repeat last part, last thing?
Can you put the, can we see that formula again for the predictor?
For the predictor means how we calculate the predicted life satisfaction. This is best illustrated by regression equation. So how about we practice how we write a regression equation for the model we just built here?
Gary, can I ask a question? I think you explained this, and I didn't catch the nuance. Along the same lines, I was using the polynomial equation from 2a, and I almost got the same answer, but it's slightly different by 1,000. So that's just wrong, isn't it? It was the it was the negative 0.0028 x squared plus 944 whatever. So that's wrong, right? We have to
okay, could you share your screen with me? I'm not sure
to.
what you mean by what you said earlier.
You have to disable sharing, and I have.
Oh, right. I didn't notice that. Somehow it doesn't allow me to check this. Well, to enable it by default, I always need to adjust it. Now I enabled the screen share.
Awesome. Okay.
So then after your question, then we can move on to build a regression equation using our model coefficients.
So
all right.
I put 6 so I use this formula here, and kind of like you're just doing. So I put 60 and I got 30.349, but this is using this formula, not what you were using.
Oh, I see. Okay, it's because of rounding errors.
So I can use this?
Well, you can, but you will be introducing rounding errors.
Do you mark off for rounding errors?
Do I? Oh, I don't grade your homework questions. The other TA who grades it, I don't think she will do so. But as I said, there's no benefits by introducing rounding errors, right? So whenever possible, it's still best to calculate predicted values using cell reference instead of typing the coefficient manually.
No, well, I'm using formula. So if I change this, to 65, I mean, it changes.
It does. So how about you move your cell to life satisfaction predicted values, then I can demonstrate what I mean. So here, let's look at, so who's sharing the screen? Stephen, right? Yeah. Let's look at Stephen's shared screen together. So notice that Stephen also used cell reference when calculating predicted values. However, the cell he referenced was as highlighted in his screen is in column G. He typed the coefficients again based on what trend line legends shows in the square in the scatter plot. However, I don't encourage you to do that because in many of our homework and exam questions, this the summary output table is required to calculate many statistics. So depending on analysis based on what a square plot shows is quite limited.
Gotcha. Okay.
But it's useful. A scatter plot and the trend line and the regression equation output in a square plot is useful for you to understand the data pattern, but it may not be enough to answer many questions that cannot be addressed solely by a scatter plot.
So I should do the regression analysis like you were doing and get those values. Okay, thank you. I didn't mean to take the time, but that explains a lot because it was so close, but not enough.
It's okay. Many times the rounding errors is so small that it doesn't really matter in terms of substantive implications. But to get exactly the same value as I did, I used the cell reference to the output table generated by regression model in Excel.
Okay, I'll do the same. Thank you.
Great. Wonderful. As you just see, there can be multiple ways to generate similar values. They are mostly okay. All right. Are there any
I
questions
guess, sorry,
about?
Jerry, not to
Hi.
go back to Stephen's question though, but I mean the polynomial equation itself already squares our value x. You know, if we take, you know, the actual, what's it, you know, y equals, you know, negative 0.0028x. So if we do not account for square of income and we just do a regression against income versus life satisfaction between those two, and then fit a polynomial trend line in there, and Excel gives us that formula. Then we use that exact formula. It already squares the income because by definition that equation is a polynomial function, so it already has a square in there. You know, sorry, that equation right there you see on your screen.
Yeah, I do.
That equation, yeah. So using that and just that equation against income and life satisfaction, against those two, against 60,000 to 70,000, and so having a different model that doesn't include the square income comes up with the same answers.
Yeah, it should come up with very similar answers. As
well,
you notice
saying, John,
here,
so if you don't have the regression square, if you don't square it ahead of time, you're getting the same answers, slightly off, but the same.
Oh, no. Okay. So let's look at your questions together. The reason why you see there's a difference between the calculated or the predicted life satisfaction between what I have here and what John and the other student, it was Stephen, I believe, showed earlier, was not because whether we squared it or not. It was because solely because of the rounding error. So notice here my coefficients have many digits. So by default, most computers are capable of calculating precision by 16 digits. And this also gives 16 digits here. The reason why you see a slightly different result was that there would be rounding error when you omit certain digits. It was not because whether we square the income or not. We always need to square the income to get a polynomial regression. Did you understand what I
yeah, no, I understand.
commented? Okay.
No, I was just taking the linear model and then but applying that with only the two variables, income versus satisfaction, and then squaring it in the equation, not.
So why do you not
income and effectively a linear model you have there?
Why did you have a separate model where you did not have a term of square of income?
Because I misread the question and I didn't.
Oh, I see. So did you
I came up
that?
with the same?
Oh,
yeah,
okay.
It worked. It seemed to iron out, I guess, in the end. But like now that I'm looking at this now, is when I made my model, I didn't have the square of income, like effectively a second variable in there.
I see. Okay, got it. So let's see what happens if we did not have the squared term. Then we need to see how to construct dummy variables. So let's build a regression where we predict life satisfaction by income alone, but not including square of income. Let's see how it differs from what we just have above. To build linear regression, it's always the same procedure. Let's go to data and use the data analysis module and choose regression. So what goes to y? Always the dependent variable, what we want to predict. And what should go to x? As I just indicated, we should not include this square of income. This is just for demonstration purpose to see what happens if we do not include the square term of income. here we do have labels, and we do want to have an intercept. So we do want to check. We do not check constant is 0. However, if we want to see what happens if we force the intercept to be 0, we can check that later. Now we just generate the output results of linear regression. Okay, here it goes. Notice how it differs to what we have above there. Let me copy and paste so we can compare these two versions side by side. Oh man, why did that happen? Okay. So on the left, that's the second order polynomial. On the right, we should call it simple linear regression. They differ by what goes into the predictors. Notice here, the predictors includes two variables, income and square of income. In the right, in the linear regression model, there's only one predictor, that's income. If we omitted the income, the square of income, notice that both intercept and coefficient or slope of income would be different than what is calculated here. This is as expected. The models would be very different when we have one set of variable versus another set of variable as predictors. Even some of them shared some common predictors. So using this model, we could still calculate some predicted life satisfaction. And you probably would have a similar outcome in terms of the predicted change in life satisfaction when income increases from $60,000 to $70,000. But the model would be very different. All right, any questions regarding why we should introduce a square term of income? Could you unmute yourself to announce the question? Otherwise, it takes me a lot of time to read through all the comments. If we
moving on to another question, unless anybody else has follow-up here.
All right. Did you also have a question regarding how to do E?
No, if nobody else has anything here, I was hoping we could briefly discuss 1D.
Okay. Let's you just joined the playlist, so let's put 1D after we address part E. So we are oh, I see. Let me take a look first. In 1D, it's about incorporating information about CT. It uses exactly the same technique what we would need to use for part E in problem 2. That's where we build dummy variables as indicators. Okay, all right. Let's demonstrate how to do part 2E, then let's see how similar part problem 1D can be as what we would need to address part E in problem 2. In part E, we have to build a few indicator, not a few, well, let's see. One indicator variable and one interaction term. So let's read the question carefully. Instead of introducing a second order polynomial term, there's another way to model the data set by distinguishing low and high income. So we should create a model where we divide 50 observations into two groups. One group belongs to the low income group, where the income is below the median income, whereas the other is high income group, where the income is above the median value. Then we create a variable to distinguish between these two groups. And also let the impact of income on life satisfaction depend on the group assignment. Then we need to explain the model and how it works. So what the question asks for is that we build two additional variables. One is a dummy indicator, the other is interaction. Dummy variable is what it means by how we distinguish between the two income group, low and high. So these dummy variables could be generated in this way using a model form, using Excel formula. Notice that it depends on whether the income is below or above median income, right? So we need to calculate the median income. And because the value would depend on the result, so we need to use an if term. So if this income is greater than the median value, so this is how we calculate median. The median value is in reference to the 50 people always, right? So we should use absolute reference. If the income is above the median, then we call it high income group. That's where we assign value 1 to this group. Otherwise, it'll be a low income group. That's where we assign 0 to this group. So using the if function or formula, that's how we can calculate the values for the dummy variable. And you can autofill it. As you notice, that's exactly how we can calculate a dummy variable. Are there any questions regarding how we can calculate a dummy variable?
No, I understand the formula. I think what's tripping me up is using the qualitative data of city names.
Oh, okay. Okay, let's see how they are similar or different. Okay, then in problem 2, we do not have cities, right? So we have only one dummy variable. As I included in my notes, there are certain principles we need to follow about how to build dummy variables. I encourage you to read them in week 4 notes about data processing. All right. Let's continue with problem 2. After the dummy variable, we also need to calculate an interaction. This is nothing but a multiplication between the dummy variable and income. So because the dummy variable equal to the dummy variable equals 0 for the low income group, so the multiplication for the interaction would be also 0. That's because we time income with 0. However, for the high income variable, the interaction term equals exactly the income because the dummy variable takes no value but 1.
Very quick question on this. So why do I need to create interaction when life satisfaction already depends on the income?
Mm-hmm. Let's go to the generated regression models where we can show it again, exactly why
you're creating the interaction.
Yeah.
No, but from the question, how did you derive that we need an interaction when life satisfaction already depends on the income?
Okay, so here is why. It says that we need to distinguish between low and high income people and let the impact of the income depend on which group. it belongs to. This would be
does.
Okay. So this will be easily illustrated in the regression model output. Let me show what I meant. Using the variables we just built, including the dummy variable and the interaction. Here is the piecewise linear model summary output. Let's show what it tells us. Okay. The model includes a series of coefficients. The coefficient
Jerry,
for income.
Jerry,
Hi?
I do not mean to interrupt, but because we're short in time,
oh, right.
I do not want to deviate the discussion.
So what's your question?
My question is, how do you derive or extract from the question that you need to create a column for interaction when essentially life satisfaction depends on income? So it says here, let the impact of income on life satisfaction depend on which income group a person belongs to. Well, it already does. So it's not that I'm letting it. It does depend.
All right. The answer is no. In a previous model, the impact of income did not, if we did not have the interaction term, the impact of income would not depend on the income group. Notice the difference between life satisfaction depends on income, and the impact of income on life satisfaction depends on something. They are quite different because the impact of the income is assessed by regression coefficient, whereas the dependence you mentioned was about the coefficient itself. Here, the question is about whether this coefficient differs between two groups. So that's why this model output is quite useful. It tells us exactly that the coefficient differs between two groups. Let's show what I meant. So there's a low income and high income group, right? So that'd be about how we construct the regression equation. So let's just do it. Regression equation. You will notice that for the high and low income group, the regression coefficient can be expressed differently. That's where it means by the impact of income on satisfaction depends on the group assignment. So for the low income group, okay, let's predict the satisfaction. So let's follow the same technique as what we did in our last week demonstration. We simply put in the coefficients here for low income group. We have the intercept. Now we should have the income coefficient. So this coefficient is 0.41. Well, 42 maybe. Times income, right? Okay, here is where the difference comes in. For the low income group, notice that how we build the dummy variable. The dummy variable would equal to 0 when it's about the low income group. So we would have about the dummy variable, right? The coefficient is 62.2, but the group value for the dummy variable would be 0. However, for the interaction, we also use the same rationale. We still have the coefficient. But the interaction, notice here, would have 0 as the Oh my God. Okay. Wait. Oh, it disappeared. Oh. Let's
Control Y will get you back there.
Huh?
If you hit Control Y, it should do undo.
It
or redo.
should, but it didn't. I guess I should. Okay, let's just start again. Somehow I didn't type the enter button. Okay, intercept. Is equal to 8.0 plus income, right? And there's also a term for for the dummy variable, but the group dummy variable would equal to 0. Now let's work on the interaction term. This interaction term should be formulated as the coefficient. Okay, but it's negative times the dummy variable value for that group is 0, and the income will come here again. So this is how we calculate the low satisfaction group regression equation. Using the same idea, we could calculate a high income satisfaction regression equation. But in this group, this dummy variable would equal to 1. So notice that these two group regression equation are very different because of whether the dummy variable equals to 0 and 1. And in the last term in the interaction, that's where it means by the difference of the difference of life satisfaction impact of income. So they differ between these two groups. Did you get what I meant?
Thanks, Jerry. So you typed income by both the dummy and the interaction. No. Okay.
Because the interaction term is exactly the multiplication between the dummy variable and income.
Yeah.
So we could simplify these two equations, right? Based on what we have in the as the dummy variable value. So to simplify it, notice that here we time 0 with this coefficient. This term cancels. And here we're also multiplying 0 with income. So this term also cancels, right? So the simplified version would be this. This has exactly the same information as the complete version, just because it removes all the terms with a value that exactly equals to 0. So for this group instead, because we have 1 to represent dummy variable value, this cannot be canceled, but instead it could be combined with the intercept term. So we have this, right? And we could also combine these two terms because both of them contains income in it. So we are doing this. All right, this is the simplified version. As you can see, the regression, the slope of income are quite different between these two groups. That's where this question matters when it mentions the impact of income on life satisfaction depend on or differ between which group, which income group a person belongs to. When a person belongs to the low income group, the slope equals 0.42. That's the impact of income on satisfaction. In contrast, when a person belongs to the high income group, the slope equals to this much. It's about negative 0.01. And the slope differs from the low income group. So that's why the impact of income depends on the income group. Are there any questions about part E? With that, you should be able to answer.
I just want to make sure that the point you just stressed about the difference between the two, and the only way to get there is by doing like a interaction variable.
Yes, exactly.
Okay.
Without introducing the dummy and interaction predictor, we would not be able to reach this contrasting slopes between the low and high groups because of this interaction term. So we can show it clearly here. If we did not have this interaction term, then the impact of the income on life satisfaction only equals to, has only one slope. It will not differ between high and low income groups. All right, with that, let's catch up with question 1 to illustrate how we can build dummy variables to represent neighborhood. Before we address any questions regarding problem 2, are there any parts you still need help with problem 2 on life satisfaction relationship with income? All right, if not, let's catch up with problem 1. How do we represent the neighborhood or the city? So in problem 1, just so everyone is on the same page, let's review the question again. We are trying to predict the house price using certain predictors. In addition to square footage, which we already used in week 3 homework question, this time we have a few more predictors, including the city where the house is located, and also the age when the house was built, and the number of bedrooms. In some earlier parts in problem 1, we already ran a regression where the predictors include square footage, age, and number of bedrooms. However, in part D, we also need to include the city location information. And also we need to explain how we did so, how we built the indicators for city. Then we run regression model, which includes information about the location, plus square footage, age, and number of bedrooms. Then we interpret the model. And also explain why it's different from part A, where we did not have the indicator of house, the city where the house is from. All right. To build the indicators, review my notes on dummy variable coding. So data processing, it's part of data processing for regression. We need k-1 dummy variables corresponding to a categorical variable of k levels. You should have already discussed this part in the lecture videos and in-person lectures. Typically, the dummy variable equals to 1 indicates the reference category. Notice that the category is seemingly missing from the dummy variable. So because we built k-1 dummy variables for a categorical variable with k levels, some of the students wondered whether whether there's any information missing by using one less dummy variables. The answer is no, nothing is missing. So this category has the reference category. It's not missing from the dummy variable creation. It's not missing in the coefficient estimates either. The information is still accounted for, so it's used in the model actually. I will illustrate what I meant here. Then using a different reference category results in a model summary that has the same R² but different coefficient estimates. This means that the choice of a reference category is arbitrary. You could use any of the categorical variables levels as the reference group. For a categorical variable with k levels, you could choose any of the k levels as the reference group. Therefore, the interpretation of the dummy and interaction coefficients would be different between these different models with different reference groups. However, the model predicting power would be the same because they share the same R². Then I encourage you to practice what happens if we build k dummy variables and use all of them as predictors. This would be left for you to do some additional exercise that we won't cover today. However, what we will cover is a typical version of how we build a dummy variable set. Let's come back to our Excel sheet. So here, what we originally got was the city name, right? So we have 4 distinct city names. Using the principle I indicated in the comment in the review notes. Out of 4 cities, we should have 3 dummy variables going into the regression model. Here, among these 4 cities, I'm mostly familiar with Lake Forest. So I would be interested in the difference between all the other cities from Lake Forest. So I would choose Lake Forest as the reference group. This choice matters in terms of how we should assign values to the dummy variables. Because I chose Lake Forest as the reference group, so all the dummy variables would be built relative to Lake Forest. That's why I named these 3 variables as the name of the 3 other cities than Lake Forest. So the value assignment procedure goes like this. This column represents whether a city is Coco de Casa. This column represents whether the city a house is in is Rancho Santa Margarita, and this column represents whether the city is in, whether the house is in Missionville. So we could use the if function in Excel to assign 0 or 1 to a case. If the city equals to Coco de Casa, we assign value 1 to the house. Otherwise, we assign value 0. To tell whether a house is in city Rancho Santa Margarita, we also use the if function. So if this house city name equals to Rancho Santa Margarita, we assign 1 to it. Otherwise, we assign 0 to it. Using the same method, we could get the value for mission vehicle. Then we could autofill all of them. So let's see what these indicators actually represent. For a city that, for a house that's located in City Coco de Casa, this indicator equals 1, whereas both of the other indicators equals to 0. For a house located in Rancho Santa Margarita, we notice that only the indicator for Rancho equals to 1, whereas all the other, both of the other two equal to 0. Instead, for a city, for a house located in Mission Viejo, only the indicator for Mission equals to 1, whereas both of the other indicators equal to 0. Now, what happens to houses in Lake Forest when I use Lake Forest as the reference group? Notice that all of these 3 indicators equal to 0 for a house in the reference group. So that's why the information that a house is located in Lake Forest is not missing. It's particularly distinguished by that all the indicator variables equals to 0. So this is how we build indicators for categorical variables that may potentially include more than 2 levels. For the case where a categorical variable only includes 2 levels, then we need only 1 indicator to represent it. That's exactly what happened in problem 2 when we used 1 indicator variable to represent a categorical variable with 2 levels, 2 levels being low and high in the income case. For the case of a city where there are 4 distinct cities, we could use 3 columns, 3 variables with values 0, 1 to represent a categorical variable with 4 levels. All right. That's so much about building indicators for categorical variables. Are there any questions?
Very quick question. If instead of Coda, we left out Lake Forest, for example, would that be okay?
Yes. Let's see what happens if we use a different reference group. So for example, I would build another indicator for Lake Forest. So using the same idea, what goes on here is that if a city equals if the city name of a house equals to Lake Forest, then we assign 0, otherwise 1. So notice here now, for a house from Lake Forest, then this column equals to 1 for lake, right? Whereas the other 3 indicators are all 0. So we could have 4 different choices of a reference group. We could use Coco de Casa as reference group, or Central Margarita, or Santa Margarita, or Mission Viejo, or Lake Forest. In my output of the regression table with neighborhood here, I used Lake Forest as the reference group. Now let's see what happens if I use a different reference group. So could you say again, what would you want to choose as the reference group?
Let me see what I did.
Or you can pick one just on site.
Yeah, I think
Which of the 4 would you want to choose as the reference?
Yeah, I had the dummies for Lake Forest, Rancho Santa Margarita, and Mission Viejo. So we could use Lake Forest.
Okay. Oh, I already used Lake Forest as the reference group. So, okay. How about we just use Coco de Casa? I know very little about this city. Okay. Now let's build another model where the Coco de Casa was used as the reference group. Let's see how it differs from the model, the regression model output I already have here, which uses the city of Lake Forest as the reference group. All right. To build a regression model, as what we did multiple times, we go to regression. Then we choose the dependent variable as house price. We also choose the city information and all the predictors. So it includes Rancho, Mission Viejo, and Lake Forest. We left the Coco de Casa outside of the predictors. Well, I'm not sure whether leaving the row index out is okay, but let me see what happens. So the regression model would be here. Okay, it seems I do need to specify particularly what's okay. Now it should work. Oh, okay, that's fine. All right, this is the output where Coco de Casa was used as the reference group. Let's put these two models side by side to compare the difference. Notice that on the left, Lake Forest was the reference group. On the right, Coco de Casa was the reference group. Let's show each part. Notice that multiple R from left to right equals exactly to each other. So as R squared, they are exactly the same. Also same adjusted R squared, same standard error, same observations. And that what we just showed here is that the model predicting power is the same. So choosing whichever among the different or multiple levels in a categorical variable won't change our predicting power of the model. However, what happens to the coefficients? We notice that from left to right, the coefficients are somewhat different. However, some of the coefficients are the same. Let's see what are different and what are the same. Here, the intercepts are quite different from each other. And here, the predictors used are also different. On the left, because the Lake Forest was the reference group, so it's not the name of any of the predictors. Instead, the other three cities' names are used as the predictor variable name. On the right, in contrast, because Coco de Casa was used as the reference group, so Coco de Casa was left out, whereas the other three cities are used as the indicators to represent the contrast. All right, does it matter to other predictors? Let's compare. In terms of the impact of the house age, house square footage, and number of bedrooms in the house, you notice that these two models are exactly the same in terms of the magnitude and sign of the coefficients for the other continuous predictors that are not about the city of a house. So that gives us a hint that using different reference group when building indicators for a categorical variable, it will change something about the intercept and the coefficients about the categorical variable, but it won't matter for the coefficients of other variables. All right, are there any questions regarding the main variable building and how to generate a model using the variables we have?
Thank you. This was very helpful.
All right. Otherwise, I also encourage you to practice what happens if you have all of these 4 possible indicators included when predicting price. So that what would happen is that instead of 3 indicators to represent the city, we use all 4 indicators. All right. I believe what we discussed already are enough to answer all of the homework questions. So I hope you enjoy a wonderful week.
Jerry, you're awesome. Thank you so much.
No problem. My pleasure.
Thank you.
Thanks, Jerry.
All right.
Thank you very much.
Have a great night.
Good night.
Thank you.
Good night. Thank you.
Night.